Here we have an amplifying op-amp circuit. What's different here is that the input voltage, or the signal voltage, is being connected to the non-inverting terminal of the op-amp. Before, it was connected over here to the inverting terminal, and we ended up with an inverted signal. Now, our signal voltage is connected to the non-inverting terminal, but our feedback is still connected to the inverting terminal. In this situation, we still have the same voltage between the two terminals of the op-amp, and we still have zero current flowing into each of these terminals. So if there's zero current flowing here, there's zero current flowing through that resistor, so the voltage drop across that resistor is going to be zero, and the voltage here at the positive terminal is going to be our signal voltage VG. And so if we have that voltage here, then we know that we're going to have the same voltage over here on this side as well. So we've got a voltage VG. We have no current flowing right there because there's no current flowing into the terminals of a op-amp. And so we have a current presumably flowing this way. We'll call that IS, is flowing from this terminal here down to ground. And then let's also say we've got another current flowing this way. We'll call this IF. That's going to be the current through the feedback portion of the op-amp. Again, there's no current here, so if we write a KCL equation for this node right here, we really only have the two currents flowing out of that node, so the two currents flowing out equals zero flowing in. This is zero right here because we're connected to ground. This voltage here is V out, the output voltage, because that's where we're measuring our output from, and so our currents are going to be VG minus zero over that source resistance, and over here our current is going to be VG minus VO over RF, if we're going for voltage difference divided by resistance. And so our KCL equation can be rewritten as thus. Now what we can do is multiply through by RF times RS. That will cancel here, and we'll end up with an RF times VG. The RF will cancel there, and we'll end up with RS VG minus RS VO. When we move the output voltage across the equal sign, this is a negative over here, it will become a positive when we move it across the equal sign. And essentially it will end up looking like that. Now to solve for VO, we'll divide by RS, we'll divide by RS, and those will cancel. And so our VO will be 1 plus RF over RS times VG. So our input is here times a gain is equal to our output. Notice that these are resistances, these are positive values, and so our gain here is all positive. We can rewrite this, find a common denominator, and more generally we'll find that our equation relating our signal and our output is thus. We just determined what the relationship was between the output voltage and the signal voltage. We have this gain factor for our non-inverting amplifier depending on our resistances here. But recall that for our op-amp to function properly, the output voltage has to be less than our supply voltages here that bias the op-amp. And so if the output voltage has to be less than this supply voltage, well, the output voltage here depends on the resistances we use and the signal. And so we can substitute this term in for our V out. That's what we see right here. And then we can divide both sides by VG. We'll hold on to the absolute value bars because VG could be positive or negative, but we see that either this expression for our gain or this expression for our gain, these two are mathematically equivalent to one another, but either one of these has to be smaller than this ratio to make sure that our op-amp stays in the linear region and it operates normally, and so that we avoid saturation.